Hi, this is the second part of Lecture 5 for Heat Transfer Mech 3820 for the summer of 2020. So what we're going to start with, or where we're going to pick off from, is looking at the heat transfer via conduction through a one-dimensional plane wall. But we're going to bring in this concept of thermal resistance and utilize an electric circuit analogy. So this is the equation that we left off with. Now again, remember, this is still Fourier's law, but I've gotten rid of the negative sign, and it's understood that TS1 is the high temperature, TS2 is the low temperature, and we'll be moving in the direction of high temperature to low temperature. So if we rearrange this equation such that we have the temperature differential on the left-hand side and the other terms on the right-hand side, we can compare this to Ohm's law. So in Ohm's law, you have a voltage potential, and that causes a current to flow through a circuit with a specified electrical resistance. So this is my voltage differential. The circuit has some type of resistance. We can typically add all the resistances to gain a single resistor for the circuit, and that will allow a certain amount of current that'll flow that's going to be directly proportional to the voltage. So we'll make our analogy here that instead of a voltage potential, we're going to have a temperature potential. Instead of current flowing, we're going to have thermal energy flowing. Sorry, this should be Q dot in terms of the watts per unit meter, right? We're looking at a flux here. And our resistance is going to be this term, and this is what we're getting to. So for a plane wall, the thermal resistance is going to be a value that is the thickness of the wall divided by its thermal conductivity. All right, so we can also apply a similar analogy to Newton's law of cooling. Again, here is the heat flux, watts per unit meter, and we have the thermal the heat transfer coefficient rather, and the free stream temperature. So this is a kind of a cartoon of what the problem would look like. So if we rearrange this again, we'll have the temperature difference on the left-hand side and the heat flux and thermal conductivity, or the heat transfer coefficient rather, on the right-hand side. Again, we can compare this to Ohm's law such that the temperature difference is the voltage potential, and again the current is equivalent to the heat flux through the wall, or I through the circuit, heat flux through the wall, and in this case the thermal resistance is 1 over H, or 1 over the heat transfer coefficient. So now if we do that, we're going to be able to analyze and this is what we're going to refer to this as a composite plane wall. So our wall now, it consists of 3 different layers of 3 different materials. Material A with a specific heat of Ka, material B with a specific heat of Kb, and material C with its own specific heat of Kc. And we're also going to allow for the thickness of these 3 layers to be variable. Outside, on either side, we're going to have a convective boundary condition, where in this case we have hot fluid over here and cold fluid over here at T infinity 1 and H1. So that's what's existing outside the left-hand wall. And outside the right-hand wall is going to be T infinity 4 and heat transfer coefficient 4. So we're basically calling this 1, and then the interface between A and B is 2, the interface between B and C is 3, and the interface between layer C and the convective environment on the right-hand wall will be 4. Okay, so in this situation, we are going to have a certain amount. So based upon, if everything's in steady state now, and I have T infinity 1 on the left-hand wall and T infinity 2 on the right-hand wall, there is, once we achieve a steady state, there's going to be a standard heat rate through the wall. And through all the layers, if there's a heat rate coming in the left wall, that has to be the same heat rate that's passing through each of these layers, and the same heat rate that's passing out of the wall. And what this will be if we look at it as a plot, if I looked at a plot of Q as a function of, Qx, the heat rate in the x direction as a function of x, it would be a constant. So the rate of heat transfer at all points within the wall is constant. But if I look at the temperature is going to vary as I move through the wall. And that's so what we're going to look at now is how do we calculate these various terms. So what we're going to do over here is, this is our wall, and say we're given T infinity 1 and T infinity 4. We're given all the information about the wall, the thickness of layers A, B, and C, the heat conduction, or the specific, not specific heats, the thermal conductivity of layers A, B, and C, and also the heat transfer coefficients that are acting in the convective environment. And what we're asked for is to find the total heat rate through the wall, and also the temperatures of the surface temperatures on the left-hand side and the right-hand side, and also the interface temperatures. So how would we go about that? Well, we're going to use our circuit analogy. So in this case, we are going to know that if I know T infinity 1, right, I've been given that. Now I don't know what TS1, the temperature, the surface temperature of that wall is, and I also don't know what Q dot is, but I know that 1 over H1 is the heat transfer coefficient. So I'm utilizing the electrical analogy for convection. But then I can apply that at the next layer. So from TS1 to TS2, this is going to be convective, the resistance here. It's basically my second resistor, LA over KA. Now notice we can leave the area of the wall in or the area of the wall out. I'm choosing to do it all as a heat flux, so I don't have the A terms in here. And same thing, from going through from 2 to 3 and from 3 to 4, it's again going to be just a conductive heat transfer. And we have two additional resistors of LB over KB and LC over KC. And the last equation is going to be the convective heat transfer from the surface of the wall 4, call it, or the right-hand wall, which is indice 4, into T infinity 4. All right, so what you essentially have here is, what do I have? I have 1, 2, 3, 4, 5 unknowns, and I have 1, 2, 3, 4, 5 equations. So it all holds together. So if I wanted to get other things, I can use other combinations. Say I've been given additional things. So if I want to go from T infinity 1 directly to T3, well then the total heat rate through the wall is still Q, but in that case I have to take into account, I'll call it resistor 1, resistor 2, and resistor 3. But sometimes you might just want to find Q dot. So say I'm given T infinity 1, T infinity 4, all the standard givens, but instead of trying to find all the internal, the 4 temperatures that provide 4 additional unknowns, I could just go ahead and say, well, the temperature differential is T infinity 1 minus T infinity 4, and that's going to be equal to the total heat rate. So like this is my V, this is equal to I, and this is my total resistance, right? Everything's in series. My resistors are in series, so they just add up. So 1 over H1, LA over KA, LB over KB, LC over KC, and 1 over H4. So kind of pretty straightforward. You have to do a couple problems to work your way through it, but it does seem to make sense. Now, just quickly, I wanted to do it that way just so we're using Ohm's law the way you might normally see it. But if I rewrite it such that I write it as I equals V over R, that's the more typical way you will tend to see the circuit analogy equations written. So on the left-hand side of all of these is Q dot, and on the right-hand side are the different ways that I can calculate Q dot. In other words, this is Q dot through the convective resistance to the left of the wall. This is the Q dot being the same Q dot that comes in, is now going through layer 1, or layer A, layer B, layer C, and then out through the convective boundary condition on the right-hand wall. And same thing, you can write it as terms of Q dot will equal the temperature differential divided by its resistances. I do make a cautionary statement here that it's easy to get your terms confused, meaning is it KB over LB, is it 1 over H4, or is it H4? Just make sure you take care of your units. If you work these units out, right, this has to be in this term watts per square meter, and this is delta T, so this is temperature, and look at the first term, I over H1. So when you invert this, it's going to be watts per meter squared per Kelvin, and my temperatures will cancel out. So again, I just want you to make sure that when you're working out these problems, you take the time to verify that your units work out. It's very easy. I mean, well, it'll be easier once you get into it, but just make sure you understand this circuit analogy, and then it's pretty straightforward to develop the equations that you need to find the quantities that you want. All right, so we'll pick up with this in the third part to look at the couple different one-dimensional situations that we have, especially looking at cylinders and internal energy generation and the like.